is okay. So it's a pleasure to me present Raphael Douady, who is currently at Stony Brook University. He will present the.
I'm more at Stony Brook. I'm back in Paris at University Paris 1 Sorbonne. But that's
okay.
fine.
Okay. Well, the program misled me. Sorry, but it's okay. So he will present SABR type stochastic volatility operators in Hilbert space. So Raphael, you have 30 minutes to present, and I will take the questions from the audience, and the floor is yours.
Thank you. So, I mean, I think if I was starting to thank IMPA for what it brought me, it would cover the whole 30 minutes and probably more. So I tried to be short on this one, but it's not because I am sure that I care less. That's joint work with Zeyou Tsao, one of my students from Stony Brook, who is actually, that's his PhD thesis, basically, and remarkable work that he did in putting together two things. One is all the work that I did earlier on Hilbert space representation of yield curve dynamics. And the other one is the stochastic volatility model, SABR, etc. So integrating the two, which raises a number of questions. There are a number of literature on the topic. A pretty good book by René Carmona on infinite dimensional model, except that I looked for my name in the book, I didn't find it. So René had to pick that in the next edition of the book. But otherwise, it's a pretty comprehensive description of all the phenomena that appear, which are pretty not obvious. Okay, so let me start by showing, what you do with infinite dimensional models in a simple case, which is the infinite dimensional generalization of the Hijron-Morton model. We can represent the yield curve always in different manners. The zero coupon rate, which I denote here by Y, like yield. The forward spot rate, which for the purpose of this presentation will be more convenient. I just take, so R of t is the same thing, whether it's the instantaneous rate. And the dynamics of the forward curve is given by a certain number of risk factors, which you can see here. Do you see my mouse when I move it here, or you just see the slides?
Yes.
Okay, that's good. You have the dynamics of the forward curve determined by the current time t and the maturity capital T, and here the maturity is frozen. So when you look at the drift, if the bond prices were depending linearly on forward rate, there would be no drift. The drift would be zero. So there is only a correction due to the fact that the zero coupon prices are a nonlinear function of the forward rate. And you see that Ito term appears like this, where you see the volatility parameters and they're cumulated from current time to maturity. It's not very difficult to do that by, there is one pretty convenient variable actually to model that. It's not y itself, but y multiplied by capital T minus t. So when you look at the dynamics of that, which is basically up to the log of the zero coupon, the dynamics is very easy to compute. And you find this Ito term to ensure that the zero coupon have a residual dynamics. Now, what happens is that suppose you have a contingent claim, you want to hedge it against all the risks. Here you have a finite number of risks. So you are going to hedge, let's say you have 5 factors. Well, a given security, a given option, swaption, whatever it is, will need as many instruments to cancel every single of those risks, because it's an option on those 5-dimensional risks. Now, if you think conceptually, there is no reason the yield curve stays within those 5 factors. You have dozens of instruments. I think you have something like 300 treasury bonds, as many. If you go to other, so you have an incredible number of instruments. The yield curve itself is a result of some fitting. So you will see the yield curve as an object in infinite dimensions, and you want to hedge the. So the volatility operator now becomes an object in infinite dimensions. So let's put that in some operator type of logic where you have now, okay, so I change now the yield curve. If I want to look at things in infinite dimensions, I need to see one object, which is a curve, and that curve therefore will slide. So the variable will no longer be the frozen maturity, but the time to maturity, which I denote by theta here. And then you have a little change when you make the differentiate with respect to capital T or with respect to theta. So you get this term appearing in the drift, which corresponds to the sliding of the curve in the dynamics of forward spot rate. The Brownian motion here is an abstract object which you can consider U is simply Rn, and it's a spherical uncorrelated volatility one set of Brownian motions here. And the volatility operator are those numbers here that you apply to go from this random set of random numbers, which are abstract numbers, that coefficient that will apply to these sigmas, to the space H where the curve belongs. So you can see that if I get some indication that my random move of the curve is given by a certain vector of dW's, here is the impact on the curve itself. So this is the curve, the real space where you have the curves, and this is an abstract space where W is simply spherical here. You get the drift again by this scalar product between sigma and its cumulated version. Now, if I go to infinite dimensions, I took these notations because this one is the notation that will allow you to go to infinite dimensions. So now let's consider F, valued in a Hilbert space. So now we are looking at the dynamics of F of T and a dot, just to say it's a function of theta. And WT now becomes a cylindrical Brownian motion in the space U. So what is a cylindrical Brownian motion? It's something that is only defined through its scalar product with elements of U. So you get sigma here. In order for that to stay within the space H, the operator sigma has to be Hilbert-Schmidt. What does Hilbert-Schmidt means? It means that the trace of sigma star times sigma has to be finite. Essentially, what you want is that if I were looking at the coefficients here that I have the sigma i's, the sum of sigma I square has to be finite so that I can add up all of those elements, all those random noise who are uncorrelated. But if I want to compute the norm of that, the expectation of the square of that, it will be dt here times the sum of square of that guy. So the sum of square of that guy has to be finite. This is pretty important because in particular, a Hilbert-Schmidt operator means that it cannot be, you cannot have, for instance, the same level of volatility on all the factors. It has to tend to zero. If it doesn't tend to zero, basically, you don't have a dynamics. Well, is that true? We will see that basically what you have is that it depends on which space, which norm you are using. And typically here for H, we are going to choose Sobolev spaces. So different degrees of differentiability of the curve. In other words, if you imagine that your curve here is decomposed in Fourier transform, you will see a sum of energy in the different frequencies of the curve. And the L2 norm will be simply the sum of those energies. The H1 norm will be the sum of the energies multiplied by n square, etc. So you see that you put more and more weight in high frequency. So the request that the sum of the sigma I square is finite is much easier to satisfy in L2 than in H1, and even easier in H1 than in H2, etc. What does that mean in practice? It means that, yes, we will have a realization of F, which is L2. Is it H1? If those factors, those PCA factors, decay fast enough, it will be in H1. If they decay even faster, it will be in H2. So you see that the regularity of the actual realization of the curve is related to how fast the sigma I that I see here in finite number, but when you go to infinite dimensional, have an infinite dimension number of them, the faster the decay, the more regular is the curve that you see as realization of the yield curve. So this is just the background so that you know what the phenomena that appear in infinite dimensions. Now, stochastic volatility model. So the classics of the famous SABR, S stochastic alpha is that alpha here, beta is this one, and rho is that one here. So what do we have? We have a dynamics of the forward rate where the volatility is proportional to the rate to some power beta. It goes from beta equals 0, which would be the kind of Hilbert-Morton, beta equals 1, which would be a BGM, beta equals 1/2, which would be CIR, etc. It encompasses all that, but the strength of it is that sigma now is no longer deterministic. It is a random process itself. And there is a certain correlation between the random process for the curve and the random process for the volatility, which is rho. So rho is determined more or less by the smile of the volatility surface of swaptions. The weakness of this is, so it's in some sense, the interest rate equivalent of Heston model for equities. And statistically, you can see that, I did that study, that for low rates, you see some sort of square root shape very clearly. For high rates, it's definitely proportional. So we see that the beta, depends on the level of the rate in general. The weakness is that it's only one factor model because these are scalar Brownian motions. So we need to fit the Hilbert-Morton. That surprisingly hasn't been done except in a paper by Fabio Mercurio inflation rates, which is not completely satisfactory to me. But anyway, so let's first make again a n factor model. Okay, I have to go fast because I see that the work, the time is okay. So basically, you just apply this proportionality f to the power beta to again a sum. So you replace the one factor model that we had here by a multi-factor, and now sigma I becomes it, and each of them have their own volatility process with their own volatility of volatility. And their correlation structure can be complicated. If I put again an operator notation, because that's what we're going to talk about, then I get the same thing, this operator here, B of TF, and B of TF, which you can evaluate at maturity theta, is this function. This one being itself, remember, a Hilbert-Schmidt operator from the cylindrical Brownian motion to the curve, the space of curves. Now you have, again, a volatility process, which is driven by a volatility structure and a correlation matrix between the two sets of Brownian motions, which now are multidimensional. Let me go fast. If we want to generalize a SABR, we did two models. One is pretty direct, where you simply have some volatility process which is not depending on the rate by itself. So it's a process in the space of Hilbert-Schmidt and multiply by the rate to the power beta. And you will see that we will require this condition, that the fourth power is uniformly bounded. That's the basic. The case of the model 2 is more complicated. Maybe I won't speak of it because we don't have very little time. It's something that Zayu imagined to better fit the requirements of generalizing properly the SABR model to multi-dimensions. But let's put it aside for the moment. More important, when you look at the dynamics, especially in infinite dimensions, you observe something which is purely statistical. You observe that there is a tendency of the curve to become smoother and smoother. That is, there is a mean reversion on the high frequencies. That mean reversion, you can materialize it by an extra term in the drift, which corresponds to something which is proportional to, so it's basically the Laplacian on the curve that comes with a coefficient that has to be positive here for the mean reversion to operate, because this has negative eigenvalues. This has been statistically proven by another student of mine who is going to defend actually pretty soon on the when does it defend? In August, in December now, 17th of December, I think. But it's not only that, I've traded it. So for those people who claim that this is not arbitrage free, indeed it's not arbitrage free, and you can make money out of it. In reality, it is arbitrage free, because as soon as you have too many factors, then the range, the strength of that term becomes completely erased by the beta spread. So you can, in reality, forget about it. But it's observable. I would say that it's still not completely incompatible with pure arbitrage-free dynamics if you make a change of variable on theta. And I like working with a log scale that is saying that the correlation between 1 month and 2 months is the same as between 10 years and 20 years and 1 year and 2 years. So it's more of a matter of ratio of maturities and distance. The Nelson-Ziegel approach, which is taking this kind of Chandra variable, has also this property of being concave. And when you make a concave Chandra variable, in the new variable, so in the psi variable, then you will see appearing mechanically, just by calculation, a term of d2 over d psi squared. So this term is important because we will need it to our existent theorem. Let me go fast because I'm missing time. Framework for stochastic processes in SDEs, that's just what we saw, what is a Hilbert space value process. So there is a covariance operator Q, and Q has to have a finite trace. So you see that Q is the covariance. So this is sigma times transpose of sigma. So Q has to have a finite trace for a strong solution to exist in H. So what does that mean? That we need to define different so here is a typical infinite dimensional SDE where this is a cylindrical point in motion again. This is this operator that has to be Hilbert-Schmidt, but that may depend on S. This is what you see with the Ito term that we had. And this one is an unbounded operator, which in our case is the first or second derivative. You see, this is this term here. A will be a linear operator, but it is an unbounded operator. So we need to put that into the picture to check, whether there exist solutions and what kind of solutions exist to this stochastic differential equation. So we have three definitions. One is the famous strong solution. So ST is a stochastic integral and satisfies the solution. And ST is H valued, and it's so almost surely has a realization in the Hilbert space H. A weak solution would say that for any H, you can define the scalar product with H. So only ST times H is defined, which doesn't mean that ST actually belongs to H. And so there is a solution ST, which may belong to some Hilbert space, which has weaker differentiability than H, in which H includes in a Hilbert-Schmidt manner. And then so you get the same equation here, but scalar product with H. And only this is valid. So this is called a weak solution. The mild solution is almost the same thing, except that you go up to, I'm sorry, because I see that the lines below are hidden, but it's basically as a strong solution, except that it's calculating from the end. So you introduce the psi of t, which is essentially e to the ta, if the integral of it just satisfies d over dt of psi of t equals a times psi. So psi of t is simply e to the exponential of t times a. And you sort out the first term, and then you calculate all of the integrals starting from the end. So when s equals t, we get psi is the identity, and it's like some sort of exponential moving average with decaying weight, because the psi acts as a regularizing. So this is a weak solution, which is basically you can verify that if you write on paper, if you were finite dimensional, it does satisfy the equation, but it's also where you would use the variation of constant to solve this equation here. And so there is a theorem that says that in general, if you have a strong solution, then it is a weak solution. If it's a weak solution, it is also a mild solution. So mild is the easiest to obtain. Weak is a bit stronger. You can verify that weak implies mild by saying, I have a solution here which I can formally calculate, and it cannot be different from the original solution, because any difference would be orthogonal to any vector in the Hilbert space, and therefore, if the solution is right, and therefore it is a mild solution. So that's that's a general theory where you can prove that weak implies mild, and you have the converse. If you know that the volatility operator, that the Hilbert-Schmidt norm, so the sum of the square of the eigenvalue, so basically the norm of G times G star has finite expectation, then a mild solution becomes a weak solution. And if on top of that, you know that you can prove that almost surely the solution is in the domain of this operator, which is your only opposition to being a strong solution when you are Hilbert-Schmidt, then a weak solution would become a strong solution. So these are, the conditions under which you can find this. So classical results, okay, I will pass on that, and I will simply go to our theorem, which is that's all with those conditions. If the fourth power of the norm of the volatility operator is finite, and if there is if the mean reversion strength on the regularization term is bigger than some minimum, then so model 2, you have a little, it's a bit stronger because there is a polynomial change. So basically you ask for more moments of the volatility operator. And I'm sorry, because again, that sentence is hidden, but there exists a mild solution. So this is our major theorem. So how do we prove that? We have to prove an inequality of this kind, which is a bit heavy to prove. So this is, that is called an a priori inequality. This is a technique that you use a lot in a functional analysis by saying, okay, so you have essentially two techniques in functional analysis to prove the existence of solutions. One, it's always comes down to some fixed point theorem. And the first technique is to put yourself in a setting, in a space where you have some contraction phenomenon. And when you have contraction, then you know that by iterating, you converge towards a fixed point, and that fixed point will be a solution to your nonlinear problem. In the case of sometimes it's more difficult. So what you define is that you prove that you have a certain relatively compact set in the space. So you use so you prove that the space that you have in the functional space in which you are working, in which you have your solution, that some relatively compact set is invariant, and to show that this is where you need those type of a priori inequality. And once you have proven that you have a convex and compact invariant set, then you apply the Loray-Schauder theorem that said that, and this is proven by tending to infinity results that exist in finite dimensions through algebraic topology. You show that there must be a fixed point, even though you don't know where that's fixed point, and you don't know whether the iteration process converges. But we have this result that shows that under those conditions, we know that there exists a solution. So why is it so important to have an existent theorem? For the following reason. Okay, I will have the idea of the proof. That's what I was explaining. I'm finishing. The reason why it was so important to have an existent theorem is that precisely when you have a numerical procedure and you do a discrete model and you try to calculate option prices, hedges, etc., with some discrete model. You could say, okay, well, I can calculate it, etc. It's exactly the same thing as calculating the kurtosis of a distribution that you know has no fourth moment. What you get is a figure, but that figure is not representative of the reality, and it is very unstable because precisely the solution doesn't exist. So all those existent theorems in functional analysis are paramount to show the stability of the numerical procedure that you are going to eventually put in place to calculate option prices, hedge ratios, etc. Thank you very much.
Thank you very much, Raphael, for your presentation. So let's open for questions from the audience.
I have a question.
Sure, Marco.
Yeah, thank you for the very interesting talk. I feel that I have to go back and learn a lot about infinite dimensional SDEs, because that's really important. And it could help make things. So let me ask you a question. Do you think that I'm not an expert in this, do you think that you had to make specific assumptions outside the Ito infinite dimensional theory using these operators, the special operators? How do you get into this? What's the key thing to when you start thinking in that way?
Well, as you could see, I mean, essentially it's controlling the growth of volatility. If you let the stochastic process for volatility grow with two fat tails for the volatility, then basically that's where the solution don't exist and you get those instabilities. Remember, for instance, there was a famous BDT model, Black Diamond model, which was purely proportional and was very unstable. And the only thing that could make it stable that Marek did with the BGM model was to say that you cannot look at the instantaneous rate cannot be log normal. Only a rate at fixed maturity like the LIBOR can be log normal. But
I'm sorry, that got frozen.
yeah, I was saying that the weakness of the BDT model was the fact that they were discretizing, so you could calculate it. It was all in discrete time, etc. But the continuous limit was didn't have a solution. And
Can I follow? Can I follow?
It was an exponential of exponential, essentially. That's the problem.
Exactly.
And the initial paper of Israel Morton, actually, they have a specification which is mostly proportional, so basically log normal, but capped at a certain level. Yeah, exactly for the same reason.
Exactly. And so, and the Marek solution, which was more appropriate, was to say, okay, let me assume that a rate with a fixed maturity, typically 3 months, is log normal, and that works. You see that because you didn't have. So you see that if you have a model, thank you, Bruno. You have a model that doesn't have a solution at the infinite limit, so in infinite dimensions, in continuous time, etc. That model for discrete time, finite dimensions exists, except that the solutions are completely unstable.
Can I ask a 1 minute question?
Yes, and yes. Please.
Is this related to the fact that the drift in HJM is quadratic in sigma?
Not only. You have to control both the
yes
drift.
Or no? Yes or no?
No,
yes?
no. You have to control both terms, the drift and the volatility term.
But there's a sigma, right? Sigma squared.
Yeah, but you really need to control it's in this equation here. You see, you need to control both terms.
Got it.
Otherwise, it doesn't work.
Thank you.
Okay, so thank you, Raphael, again for your great presentation. It's a very interesting topic, and I'd like to invite everyone to join us in our virtual coffee break. And I guess
Thank you very much, Alan. I want to say that Zeyu is participating, so you will be able to ask him also questions during the coffee break. Yeah.
okay, so yes, we have the link for the chat room is in our webpage, and I invite you to join the coffee break, and we resume our seminar in 20 minutes.